Capillary fiber membranes are the only membrane elements that are not made from flat sheet. They're made by spinneret technology, and they're actually a polymer that is unsupported, and these are down in the millimeter range, 1, 2, 3 millimeter ID. And the feed can either go on the interior of the lumen and the permeate come out through the wall, or vice versa. You can actually have the feed come in on the outside of the hollow fiber, and it goes through and is purified and comes out that either way. And then plate and frame, which we don't see much anymore, except when you get into membrane bioreactors. This is a tubular membrane. This is one that's actually made in the Netherlands. These are 1/4 inch tubes. This is what it would look like. This could be, this is about an 8 inch diameter vessel, and they can be up to 10 or 12 feet long. This is a hollow fiber, and as I said earlier, you could either go into the feed on the outside of the fiber and come out one end or the other, and these are exposed openings, hollow fibers that the ends have been cut off, so they're exposed, but they're potted in an epoxy to keep the cross-contamination between the water coming in here and the water coming out here. And the spiral wound, which again, the manufacturers don't particularly like this analogy, but it's like a roll of 2 layered toilet paper, basically. You have 2 layers of flat sheet it's a non-woven material with a polymer coated on one side. These 2 layers are sandwiched together, and they're sealed around the outer edges, so the only way water can get in between the 2 layers is to have to go through one of the layers. It's collected there, it passes in a spiral fashion down to the center. You can just barely see these openings here. This is in the tube, what's called the permeate tube. The purified water goes into the openings and comes out one way or the other. Without having one in your hand, it's a little bit hard to envision these. This is a couple of different plate and frame devices that are commercially available. And the comparison between these configurations is based on 2 factors. Packing density, how much area of membrane per unit volume can you get, and what is the fouling resistance. And you'll notice these are just the opposite. The tighter you make these packages so that you get more area into it, the more prone it is to fouling. And that's why the spiral is the most prone to fouling of all of them, really. And then this illustrates the system. And I don't want to get too deeply involved in membrane technology, but the characteristic of all of these membrane technologies is a factor called recovery. It's that percentage of the feed water flow. It has nothing to do with rejection or quality now. The percentage of feed water flow that passes through the membrane and is purified and becomes permeate. And that is known as system recovery. And that is up to the system designer. That's his purview to put any recovery he wants into the system design. Those of you who've been exposed to reverse osmosis might have heard people say, oh, well, you know, the trouble with these under sink units is they waste so much water. And, you know, here we are talking about water reuse. Well, what's going on here? We're throwing as much as 75% of the water that comes into the system down the drain. That's true. But keep in mind that all of these point-of-use RO systems have automatic shutoffs on them, so they only throw water away when they're making water. And the typical family may drink a gallon or maybe at the most 2 gallons of water a day. So that means at the very most they're throwing away somewhere between 4 and 8 gallons a day down the drain, which of course could be collected and reused because the total dissolved solids concentration of the concentrate stream is only about 30% higher than it is of the feed. So this is perfect water for reuse. But anyway, that's recovery. And when you're dealing with wastewater, such as water reuse, you have to you want to operate these at high recovery. So you have to be sensitive to the fact that if you increase the concentration of salts in the water, you can get scaling. You can get a phenomenon known as osmotic pressure, which is a function of the salts concentration. That's why you hear about seawater desalting. The maximum recovery now, even today, is only about 50% on a seawater desalting plant. The good news is the plant's right on the edge of the ocean, so you can easily discharge the concentrate back into the ocean. But the reason why is because it takes 400 psi of pressure on a normal seawater application to get your first drop of water. So these normally run at between 800 and 1,000 psi pump pressure. And that's due to this phenomenon called osmotic pressure. And because it's always a percentage, and I don't want to spend the time getting into this in any detail, but as you go up in recovery, the permeate quality in terms of total dissolved solids goes down. And then as you go into high recovery, particularly for wastewater streams, you have to be sensitive to the fact that the concentrate could be a discharge problem. And most of the applications I get into for using membranes for wastewater is the reason they do is because they want to concentrate, usually a hazardous waste, into as small a volume as possible. And it's possible to go to 90 to 95% recovery, which means now you've got that volume of material you have to get rid of down into 1/10 or 1/20 of its original volume. And then the last thing I want to talk about is this groundwater reclamation system in Orange County here in California. To me, it's a groundbreaker because it is the first application I'm aware of in the United States where the municipality overcame the yuck factor. They did an excellent job of bringing the community into this and pointing out that we're taking your secondary treated sewage, we're going to clean it up, and we're going to put it down in the aquifer. Where's the drinking water coming from? The aquifer. It's also holding back seawater to prevent seawater intrusion, but it's still a source of drinking water. And what this uses is secondary effluent from the Orange County sewage district going through screens, through microfiltration, then through reverse osmosis. The microfiltration cleans up the suspended solids so that the RO will function without undue fouling. Goes through, it's actually called advanced oxidation, hydrogen peroxide and ultraviolet irradiation, and basically going into the aquifer. It's an excellent system. It's now running at 72 million gallons a day, and they're in the process of upgrading it to 130 million gallons a day, I believe. So it's the first example. This is exactly what is happening in Singapore for what they call their new water. And so something I coined because my company name is Cartwright Consulting Company, 3 C's. Here's conservation, collection, and conversion. And it requires commitment. So thank you very much.